Okay, I think we should go ahead and get started now that we're kind of filling up and it's 9:02. So good morning, everybody. My name is Kelly, and today I have the pleasure of hosting Katriona Edlmann, who is with the University of Edinburgh. And she is going to be giving a talk today on her research in hydrogen storage. So let's read her bio out real quick. Dr. Katriona Edlmann is the Chancellor's Fellow in Energy within the School of Geosciences at the University of Edinburgh. She studied petroleum geology at Aberdeen University before undertaking her master's degree and PhD in petroleum reservoir engineering at Heriot-Watt University. Katriona is a geoscientist with 25 years experience researching the secure and sustainable utilization of the subsurface for low carbon energy applications, including carbon capture and storage, hydrogen energy storage, and geothermal operations. She is co-investigator and work package lead on 2 UK and EU funded projects researching the feasibility of large-scale geological storage of hydrogen in porous rocks, supporting the advancement of hydrogen as an energy transition pathway to reduce greenhouse gas emissions to net zero by 2050. She currently serves as the ETP Deputy Hydrogen Strategic Theme Champion, which sounds awesome, and is a member of the Gas Goes Green Academic Challenge Forum. So before I turn this over to Katriona for her presentation, I just want to go through a little bit of logistic stuff. So you guys, please hold your questions till the end, at least verbally. You're welcome to write your questions in the chat box. And then at the end, we'll open up for questions. And for those of you who will leave before we get to the very end of our seminar, please be in mind that we have no seminar next week due to Thanksgiving, but the following week on December 3rd, our seminar speaker will be Alton Brown, who will be speaking about his work in the Strawn Formation of North Texas. Okay, Katriona, please take it away.
Oh, thank you, Kelly. And yeah, thank you for that introduction. Right, let me share my screen first, which might take me a couple of steps because I normally have multiple screens, but I don't. Okay, so hopefully that's you seeing a full screen now from my computer.
Yep,
that's
you are good to go.
Very much. Excellent, excellent. Well, that's great. So yeah, so thank you very much, and thank you to you all for inviting me to come and sort of present an overview of some of the work that we've been doing in geological storage of hydrogen to support net zero. And really to delve into some of our kind of research findings, which I thought you might be interested to hear. And that's really the extremely talented team of researchers that investigate hydrogen storage in porous rocks that I work with at Edinburgh University. So they're all listed on that slide. And as Kelly mentioned, we've got 2 current live EU and UK funded projects looking at this. So the HyStorPor one has been running for 2 years now. So we've got some really nice findings from that, which I'm going to share with you. And then the HyUsePre is the EU project, which is really a bigger and better version of HyStorPor, again focused on the porous rocks. So really looking at that idea of repurposing depleted gas fields or aquifer storage. And we're also doing some work to map the geological location of onshore and offshore depleted gas fields, saline aquifers, and engineered salt caverns as well. So we do quite a lot of work with salt caverns as well, but I won't cover those today. And what we're really trying to do is build a GIS-based hydrogen storage map for the UK. And this has been commissioned actually, interestingly, by one of our gas network suppliers. So they're really looking forward to the, well, they have to look forward to the to change their kind of business. So they're really looking seriously at where they can store hydrogen if they're going to repurpose the natural gas network for hydrogen. So that's quite a nice one to know that industry are funding this work as well as the as well as the funding bodies. So yeah, so that's really where we are. And I don't need to tell you this. I don't even know sometimes why I start with this slide, but I think it's quite useful just to kind of conceptualize it. We really do need to cut our emissions. That's the bottom line. They account for over 3/4 of the emissions that we have, related to energy in industry, transport, and domestic use. So we really need to do something with this. And we are making good progress, or we're making some progress, should I say, in reducing emissions through our energy efficiencies and, of course, our increased renewables. But the picture on the right, which is from the carbon brief showing past and future CO2 emissions by sector in the UK, that is anyway, it shows the red line with the electricity shows that, of course, we're making great progress with the electricity, but it's not hitting the other sectors. And that's really not going to be enough to reach our net zero targets, particularly in the kind of harder to abate sectors such as transport and industry and heating our homes. and we need these new decarbonisation pathways, and of course green hydrogen from electrolysis of water powered by excess or dedicated renewables, or blue hydrogen generated from the reformation of hydrocarbons with carbon capture and storage, has been identified as a low carbon alternative to fossil fuels, and to help us really achieve that necessary decarbonisation of energy and reach, well, certainly the UK net zero targets of reaching net zero by 2050, which is enshrined in law. So judging by the progress we're making, I do not know how we're going to achieve that, but we have to. So things really need to pick up pace, and that's really kind of why we're doing this fundamental research at this early stage. And again, why hydrogen? Well, we really do think it's going to, it's certainly playing a part in all of its, all of our future climate modelling for the UK and in the EU indeed as well, does now include hydrogen. That wouldn't have occurred, well, that didn't occur 3 years ago. So this is really, hydrogen has really found itself on that kind of climate mitigation and future energy use really very recently. So as I say, it's really only appearing in the last couple of years, and there's been a lot of work building hydrogen into our kind of future energy scenarios. Primarily because, as I mentioned, that hydrogen can do two things very well. It can enable the increase in our electrification and our through renewables by supplying that essential energy storage to buffer the large seasonal fluctuations in energy supply and demand, and cover those periods when the supply is outstripped by demand, and of course tackle these hard to decarbonize areas. So that's really what we're looking at it for, and things like replacing the methane in our gas grid to decarbonize our heating and the industry, deliver our necessary long distance transport range, and of course replace hydrocarbon based industrial processes such as in steel making. So that's really where hydrogen is kind of, it's these hard to abate sectors and supporting increased renewable energy generation where hydrogen is really kind of finding its place. So it's not a replacement, but it really is a supporting technology, I think, for our existing decarbonisation plans, and that's where it sits. So that's kind of why we're looking at hydrogen, and the world is looking to hydrogen, the landscape is looking quite positive. So it's slow, but it's positive. So we've got over 30 countries setting out hydrogen policies so far. I think, well, Scotland and the UK have just announced theirs over the last couple of months. And there's about $300 billion worth of clean hydrogen projects already underway or in planning. So there are a lot of pilot projects happening. And as I mentioned before, we really do need, in all our climate, certainly in all the UK climate neutrality scenarios, by net zero, to reach net zero by 2050, we have a growing reliance on hydrogen. And as I say, we have a couple of hydrogen policy statements from the UK and the Scottish government. We have a green industrial revolution. I don't know whether the US is doing the same, build back better and build back green. So we have a lot of support in that. And hydrogen is one of those key points in that 10-point plan that we have in the UK, certainly. And of course, we have we have a North Sea transition deal, which really wants to support the transformation of the oil and gas sector in the UK to a net zero future, so that we're not really, we're not finding a huge unemployment in these areas, and that we're really trying to repurpose and reuse these skills and knowledge, which of course hydrogen can do so well. And a particularly effective driver of the hydrogen economy are these clusters or valleys. So they create little mini hydrogen economies, and we have about 30 of those across the world. And in the UK, we've actually got 2 that have been given significant funding and the go ahead. And these are kind of industrial clusters centered around blue hydrogen production. I'm not quite sure why they're focusing on blue hydrogen production, but certainly they're focused around blue hydrogen production with carbon capture and storage, and of course carbon capture and storage from industry as well. So we're really looking at these kind of low carbon industrial clusters. So yeah, we have 2 of those that are hoping, well, the aim is that they're going to be deploying hydrogen and CCS, blue hydrogen and CCS by 2025. Which is not that long in the future. So these are happening as we speak. And then I noticed, actually, I was speaking to somebody recently, and they were mentioning you have the North Dakota Hydrogen Hub, which I think is a very similar idea, that you've got these kind of industrial clusters where you've got that produced, storage and transport of blue hydrogen, and then capture and sequestration of CO2 in offshore assets. And I think that one is planned for 2026. So again, these are you know, these are happening. Well, let's hope they happen in these timeframes that they're going to do. Okay. So I really want to kind of, you know, why we need geologists in this. Where does the geology come in? And I think that's really kind of the central role of geological storage in enabling this hydrogen economy, particularly at the scales required for net zero. You know, surface tanks are fine, but really to get the real scales of deliverability for hydrogen, we need geological storage in some form of another. And that's really kind of the focus of our research, is doing the feasibility studies for that, so that when we're ready to go, all of the kind of you know, that fundamental science is on its way to being well established, and hopefully with pilot projects tested and shown to be commercially possible. So if you look at the figure on the screen, which I'm probably sure you've seen many times, but we really look, which shows discharge time against power. For hydrogen, we can see that the surface tanks can deliver kilowatts to megawatts from minutes to hours. Which is fine, really important for grid balancing, and that gives a storage capacity of about 10,000 kilowatt hours at the most, which is a single household gas usage in the UK. So we're going to need a lot more storage than can be held in a tank to reach net zero and deploy hydrogen at the scales we're going to need. And that's going to rely on some form of geological storage, so that whether that's engineered caverns in suitable rocks, our salt caverns, which are capable of gigawatt storage discharged over days to weeks. And when you've got many salt caverns stacked up together, then that can go up into the terawatt hours, and then ultimately onto the storage in these deep porous rocks, such as depleted gas fields and saline aquifers, which can hold that terawatt of storage with discharge over weeks to months, which is really what we might require in the future. So if we consider how much hydrogen we are likely to need in the short to medium term, this figure was based on a EU kind of fuel cells and hydrogen joint undertaking report, and it was analysing the opportunities for hydrogen technologies to reach 2030 emission targets. And they anticipated a hydrogen storage demand of around about 20 terawatt hours. And that was actually only for a moderate scenario. So that was 20% hydrogen blending, some contribution to power generation, and moderate use in transport and industry. So this wasn't a full hydrogen scenario. And as you can see on the slide, you know, if we look at the way natural gas is stored, for example, then a lot of that storage is in the high pressure transmission line packing. But of course, because of the densities and whatnot, energy densities and properties of hydrogen, that would really actually need about 90,000 kilometres of high pressure line packing, which we certainly don't have in the UK. We have these lovely, huge, big surface tanks from the old days when we held our gas in localized areas. So there's big blue, they're lovely, just really iconic looking kind of gasometer tanks in the UK. And again, we'd need about 70,000 of those. So again, that's quite a surface footprint. We'd need 400 medium-sized salt caverns or 1 medium offshore depleted gas field. So it really highlights that large-scale opportunity that geological storage can provide, particularly in these porous rocks. Although it's always worth caveating that with we're going to need them all. You know, to give us the required flexibility in the hydrogen grid, we're going to need all of these storage options, as we currently do with natural gas. And salt caverns are going to be a very likely starting point for that, mainly because of the operational flexibility and experience. They're already at high TRL levels, with salt caverns already in commercial operation for hydrogen. And while we do some work on hydrogen storage and salt caverns, I'm going to focus on the work we've been doing on porous rocks, and really, you know, to really maximise our renewable resources over interseasonal scales and reach that deep decarbonisation that we need. So yeah, the kind of next question to ask, which I'm sure you'll all be aware of, I can probably skip through this one quite quickly, is what experience do we have of using the subsurface for energy storage? And if we look to natural gas energy storage, we have masses. 1,000 terawatt hours of global gas storage facilities already in operation around the world. So this is an extremely well developed technology with an established supporting infrastructure and management in place. So we have over 670 underground natural gas storage sites in a range of different geological settings. of course, over 90%, significantly in porous rocks. So nearly 90% are in the porous rocks of depleted gas fields that have switched from production to storage or within deep saline aquifers. And then we have the salt caverns, which take up about 12% of those. What's interesting about the salt caverns is that while they hold 12% of that kind of natural, of that capacity, of that storage capacity, they have the ability to do the high injection withdrawal rates, so they can be cycled several times a year. So although there's 100 caverns in operation around the globe for natural gas storage and holds, as I say, about 12% of our global gas capacity, their rapid cycling actually means they provide up to 20% of our stored natural gas delivery. So I think these are kind of, you know, it's undeniable that these are really flexible resources that I think will really play their part in the hydrogen storage. But of course, they're limited geographically, so it's not something that we all have. So we really do have to look to the porous rocks as well. We have a few remaining storage facilities within engineered rock caverns and abandoned mines, which are important bespoke solutions, but I think that they're unlikely to be deployed at scale. But certainly there are options for places where they don't have the salt or the porous rocks. Okay, so the next slide. So yeah, now we talk about hydrogen storage in subsurface rocks experience and what do we have. And actually we have surprisingly quite a lot. So because we've got plenty experience in geological storage of natural gas, but actually, you know, we do have quite a bit of practice with storing hydrogen. It's been stored in the salt caverns for the use in the chemical industry since the 60s, starting in Teesside, or certainly one of them is in Teesside in the UK, and then you have the others in the US at Clements Dome, Moss Bluff and Spindletop. So these are kind of active salt caverns storing hydrogen commercially, which I think is a very good sign because they've been running since, well, certainly the one in Teesside has been running since the 70s. So that bodes well, I would say, for hydrogen storage. We also gained a lot of experience when we stored town gas, which we produced from the gasification of coal, which was about 50 to 60% hydrogen. And these were stored in deep saline aquifers in France, Germany, and the Czech Republic in the 60s and 70s. And these were stored, this was when town gas was used, of course, before the North Sea natural gas came on stream and replaced town gas completely. And actually many of these storage reservoirs have now been converted to natural gas stores. So they certainly were operated with hydrogen for many years successfully and again commercially. And then we have two really interesting projects, which I'm sure you've come across, but if not, they're worth looking out for. They're basically looking at the production of biomethane in the subsurface from hydrogen and carbon dioxide using the bacterial conversion from the microbes in the subsurface. So that's the underground sun storage project by RAG in Austria and the HyChico project in Argentina. So they are injecting sort of about 10% hydrogen into porous reservoirs for this biomethane generation. And while they're using up or trying to use up the hydrogen for biomethane generation, they are gaining really important experience in hydrogen injection and storage in the subsurface. So they're really interesting projects that are actually quite generous at sharing their learnings, so that's really encouraging. And then the last one which we have is the Swedish hybrid project. So of course Sweden isn't really renowned for its porous rocks or its salt caverns, so they are actually planning to develop a 100 cubic meter hydrogen storage capacity in a rock cavern, so hard rocks about 30 meters below ground level. So they'll be engineering a cavern for hydrogen storage, and that hydrogen is for use in a steel decarbonisation project. So that's ongoing. So they're already producing completely decarbonised steel from hydrogen. So this storage capacity will enable them to upscale their production and see how that's going. So I think that's going to be a really interesting project for countries without depleted gas fields or porous rocks and suitable salt caverns for storage. And I recently learned about I think it's the University of Illinois, their future, Gas Technology Institute. They're investigating the feasibility of hydrogen storage within the University of Illinois footprint in the Mount Simon sandstone. So I think that's going to be an interesting one to watch if they get the go ahead for that project as well. And I imagine there's projects around the world which are progressing. So it's great to be talking to you, and hopefully we can kind of share some of our experiences within that, in the experiences that we're learning. So if we go back to hydrogen storage in porous media, really, how many stores are we going to need? What's the storage capacity of these, if we are to convert our existing natural gas reservoirs to hydrogen? And that was really one of the questions we thought, well, how many of our North Sea fields would we need if we were to switch to hydrogen? So we undertook a storage capacity estimate for hydrogen storage in the depleted gas fields in the UK North Sea. And we based it really on our anticipated energy storage. So we wanted to know how many fields we'd need to store 80 terawatt hours of hydrogen. That was our target figure. We wanted to know how many fields were going to be that, how many fields we were going to need. So on the figure on the left, you can see the blue dotted circles on the land. So these are basically our energy storage needs to meet heating by region. So our heat is delivered in regions. So that's the blue dotted circles on the land. Those are the storage needs by region. The blue lines are the main gas pipelines that are linked to our existing gas terminals, which are shown as triangles. And then the circles offshore are the calculated and scaled hydrogen energy storage capacities in terawatt hours. So the larger circles reflect greater storage capacity, and they're color coded to the terminal that they would serve. And as you can see from the scale that's shown, our results indicate actually there's thousands of terawatt hours of hydrogen storage capacity in North Sea depleted gas fields. And actually, in reality, we might only need one or two to store enough energy as hydrogen to balance certainly the UK's seasonal demand for heating. Obviously we'll need a lot more than that, but that was we just wanted to know if we were to balance our heating demand. So that was kind of quite positive, really. And then my colleague Ali Hazanpour Yuzband, he further developed this work to look across the globe, to look at primary energy consumption by country, and matched it to the calculated hydrogen storage capacity of almost all the known giant gas fields. So that's the figure on the right. Again, the blue circles scaled to field storage capacity, with larger circles reflecting greater storage capacity. And the countries are shaded by their energy consumption, with darker colours reflecting that higher primary energy consumption values. And as before, our estimates are continuing to suggest that really one or two large depleted gas fields per country will supply sufficient storage capacity for their entire seasonal demands. But it's very important to recognise that these are both their volumetric capacities. So although we used original gas in place and recoverable gas production values, so they're one step above an actual volumetric capacity estimate. These were only for methane, so they're not spot on yet, and really we're only going to be able to get these accurate estimations of hydrogen storage capacity when we match them against operational data during active geological hydrogen storage projects. And we've not assumed a cushion gas at the moment yet, because I'm sure anyone who's working in the field of hydrogen storage, and when it comes to say, well, how much cushion gas are we going to need? You'll see numbers between 10% and 80%. So we haven't really, we haven't tied that down yet. So these are, these are quite, these are very much first order figures, and they need to be tied down. But it is, again, it's just encouraging to show that these, these numbers are showing that the porous rocks can certainly deliver the scales of hydrogen storage that we need. So of course, that's great, but now we need to make sure that it works. We need to really establish the fundamental feasibility questions of hydrogen storage in porous formations, and that's really the aim of the EPSRC for our UK-funded HyStorPor project and the HyUsePre project. So we just started by asking the very basic questions. We wanted to understand, if there's any biological or chemical reactions between the rocks, the existing reservoir fluids, and the injected hydrogen that could compromise the storage. So be that through geochemical or microbial reactions that might dissolve or block up the pore network, or consume or contaminate the hydrogen. So we really wanted to understand that. We also really need to understand these flow processes that will influence hydrogen migration and trapping during injection and withdrawal. Essentially really to make sure that we can get the hydrogen that we inject into the reservoir back out again over multiple cycles of injection and withdrawal. We also undertake reservoir simulations to really understand what volumes of hydrogen can be stored and recovered from storage sites, looking at the cushion gas amounts, determining the kind of injection and production rates to try and minimize cushion gas mixing, for example, if we're looking at hydrogen storage in a methane reservoir where we may get mixing between the hydrogen working gas and the methane cushion gas. And really understand how we can avoid any mechanical degradation of the reservoir and the cap rock during these cycles of injection to look at optimizing the hydrogen production through the wells and deliver the withdrawal rates that we're going to need to feed the energy system. And then, of course, last but certainly not least, is to understand what citizens and opinion shapers think about hydrogen storage and its contribution to achieving net zero. So that's a really important dialogue that we need to have and work towards basically making hydrogen almost every day. I always think we need to make it a bit boring, really, so people kind of get used to it and don't, it's amazing how many times I'm asked, yeah, but hydrogen's flammable, and you think, well, so is natural gas. So, we really just need to kind of understand that role of hydrogen in that wider, in people's wider understanding of the energy system. So I want to just start with the work we've been doing on our biological reactions and just delve a little bit deeper into some of the findings that we've had on the HyStorPor project. So this is a really big question, understanding the biological reactions that may result from hydrogen injection into porous storage, into porous reservoirs is really important. Well, we've seen already there's two projects almost utilizing that commercially to produce methane. So this is a big concern that may impact the feasibility of a hydrogen store through hydrogen losses, whether that be consumption or contamination, and biofilm pore blocking, reservoir damage through mineral precipitation, and of course degradation of any operational equipment and potential environmental risks. If we have, say, for example, H2S, produced during that process. So we really wanted to get a handle on what might be the consequences or likelihood of the biological reactions. So my colleague at Edinburgh, Katriona, so basically what she did was she undertook an extensive study into the life limits of the 3 key hydrogen consuming bacteria. And I'm glad I'm not a biologist because I can never pronounce them, but it's the methanogens, the homoactogens, and the sulfur species reducing microorganisms. So what she looked at really was their limits of life to temperature, to pH, and to salinity, to really understand kind of what conditions they're going to be comfortable at and what conditions they may not be comfortable at. So her findings from her work suggest that actually any storage reservoir with temperatures over 122 degrees or with salinities above 4.4 molars, NaCl equivalent, or fields that have temperatures above 55 degrees and salinities over 2 molars, NaCl equivalent, will be less favourable to microbial growth. So I think the next slide, nope. Oh yes, it's this one. Yes. So basically, what we're starting to think is that these limits, these life limits, could be applied as a storage site screening, so we can select sites almost to minimize that risk of microbial activity. So with these limits in mind, we overlaid the temperature, pH, and salinity conditions over our North Sea fields. And basically a large number of our North Sea gas fields have conditions unfavorable to microbial growth. I actually just a couple of days ago did a calculation. So we looked at 207 fields for salinity and temperature, and of those 74 could almost be considered sterile for microbial activity. So that's quite an encouraging kind of first pass, that these fields plotted above the temperatures, above the salinities, or within that, or above that lower salinity and temperature. So this is really quite, this is really quite a positive outcome, I would say, that we had these, these 67 fields that were really not favourable to microbial growth in the North Sea alone. Again, as with everything, there's always a caveat and there's always more research needed. And it is important to highlight that this analysis was based on a death study on cultivated species and studies on deep subsurface microbial ecology, not directly on hydrocarbon reservoirs. So I would say that this is really very much the beginning of a journey understanding that interplay between hydrogen storage and the subsurface microbiology. So all of this work has been written up in a paper, and the link to that paper is at the bottom of the slide. And I'm very happy to share the slides and sharing of these papers as well, if you need access to them. So microbial reactions, our first indications are quite positive. We do feel that there will be life limits to the bacteria that may play into the, into our site selection process to minimize the risk of the microbial reactions. So then the next thing to do is look at geochemistry, because of course changing the reservoir pressure and temperature during hydrogen injection and production, coupled with a dissolution of, well, minimum amount of dissolution of hydrogen into formation fluids, may induce mineral reactions which alter the cap rock, the reservoir, and of course well cements and casing integrity over time. So we really wanted to understand these potential geochemical induced changes to porosity and permeability that may create leakage pathways or impact injectivities. There are a few known geochemical reactions that are influenced by hydrogen. These include the pyrite-pyrrhotite transformation, which could release the hydrogen sulfide gas, which increase water pH and consequently changes the activities of the formation fluid, promoting further mineral reactivity, and of course increase the risk of corrosion risk to operational facilities. And increased hydrogen concentrations in porous reservoirs can also promote redox reactions, resulting in the oxidation of hydrogen and the reduction of electron, etc., such as nitrates and ions and sulfates and geochemicals. So we really wanted to get a handle on the likelihood of these reactions, because they're shown in modelling, but we wanted to know what do they actually happen in within a kind of controlled laboratory environment. So my colleague Ali Hassanpour Yuzband, between us, we designed and developed and commissioned a suite of we built a set of high pressure and high temperature batch reaction vessels. So these are capable at temperatures up to about 80 degrees centigrade, pressures up to 55 megapascals, with rock samples ranging from powder to cylinders up to 60 millimeters in diameter, over a range of salinities. So we can really bring these, we can bring the reservoir conditions to the rock samples to test them. So we've tested over 200 different samples so far from a huge range of sandstones, cap rocks, well cements, and pure mineral phases. And we've really tried hard to get a reaction. We've powdered, we've disaggregated, we've really done our best. We've left them for a very long time. We've done our best to get a reaction. And so far, from all of these experiments that we've done with hydrogen at reservoir conditions of pressure and temperature, we've never yet observed a significant geochemical reaction. So again, more good news for geological storage. This work is just currently in submission to Joule, so hopefully we will hear soon whether that's coming out. But certainly, the early indications are again positive for hydrogen storage, that we really aren't seeing very many reactions in the laboratory, no matter how hard we try. So next slide. So yeah, of course, one of the things we really need to be cognizant about is the sealing capacity of the cap rock. These depleted gas fields are sealed with hydraulically tight, low permeability cap rocks, which prevents the gas migrating upwards. So we really want to know whether they're going to seal for hydrogen. So we did a kind of quick calculation. We tried to do a column height calculation conversion to derive hydrogen column height. So how much sort of column or depth of hydrogen these known reservoir cap rocks would hold, based on their methane column heights. And this conversion factor is based on a methodology that was developed by another colleague of mine, actually Mark Naylor, Edinburgh, for CO2 storage. So we kind of adapted that for hydrogen. So the equation at the top right of the slide, that's the one that we use to calculate the conversion factor. So it accounts for the density difference between the gases with saline water at reservoir conditions, the interfacial tension ratio, and the wettability difference between the two gases with saline water under reservoir conditions. And again, all of this work is written up and can be found in the link at the bottom of the slide. And as you can see for the graph at the bottom, if you look to the green line, which represents the generated hydrogen column height conversion factor with depth, we can see that really for all depths, that conversion factor is calculated to be greater than 1. So that indicates that hydrogen can be, in theory, be stored at a higher pressure in the reservoir than methane, which again is encouraging news for the geological storage of hydrogen. But as always, a caveat that makes sure that we need to ensure that the reservoir pressure isn't increased above pre-production pressures to minimize that risk of geomechanical failure in the reservoir. And just keep that system kind of managed as best we can. So caprock sealing is also encouraged. There's also some more work by my colleague Mark Wilkinson. So they did some very nice diffusion calculations about the loss of hydrogen through diffusion into the caprock, and they estimated it to be millimeters, very small risk of that. Another good sign for the caprocks that the diffusion losses are going to be minimal, and we know that they can hold a comfortable caprock sealing. So the next work that we've been doing in the HyStorPor project is to visualize the flow, and this is really exciting and really interesting, just to see how that hydrogen inhabits the pore space, and really try to do some X-ray micro CT visualization of hydrogen flow. So this is work that's led by my colleague Eike Thijssen of the bacteria fame. So we have designed and built a bespoke cell, an X-ray transparent cell, for 5 millimeter diameter core samples. So we found that 5 diameter sandstone core samples is really the most optimal sort of balance between resolution in the micro CT, because the smaller the better, but of course we've also got to capture that pore volume representativity. So that's why we've gone for 5 millimeter diameter. We did quite a lot of testing with lots of different diameters and sandstone types, really to make sure that we could get that balance of good capture of pore network. So we use these 5 millimeter diameter Clashak sandstones, which are the ones that we've been doing a lot of this work on, and you can see already that these are some of the kind of captures of some of the imaging of the hydrogen flowing through a brine saturated pore network, and we're observing that it behaves really. It behaves very similar to any gas, and it sort of dominates the center of the pores. But this work has actually just begun, and we're really only just beginning to interpret it. We actually went to our diamond synchrotron, so our diamond light source synchrotron facility, to undertake time resolved imaging of the hydrogen flow. And Eike came back with 55 terabytes of data. So she's trying her best to work through that as quickly as she can to get some of these findings out, so that we can really understand the dynamic flow of hydrogen and visualize that dynamic flow of hydrogen through the so hopefully we can get that out to everybody as soon as possible, because it's really kind of it's great visualization that Eike has done on that. So we're keen to share that information as quickly as possible. So what I do want to do here is present some, so in support of the X-ray CT work and that pore scale network understanding, again, my colleague Ali has been doing some pore scale modeling work. So they've undertaken a sort of 2-dimensional multi-phase, multi-component lattice Boltzmann simulation to model the migration of a hydrogen plume in a water-saturated porous column. I don't want to go into the details of all the modelling because I am not a modeller, but Ali's email and his colleague Murhadid are on the slide if anybody wants to talk to them and learn more details about this. So speaking as an experimentalist, I find it rather annoyingly, I am rather annoyingly going to let modelers sort of almost steal the show with their videos, but I think they're really kind of important, and really, they're a really good demonstration of visualization of hydrogen flow. And as I say, this is kind of supporting the work that we're doing on the X-ray CT scans. So both videos show hydrogen flow in blue through a fully water saturated column of orange, with the grains in paler orange. So the model on the left shows a water saturated column in orange of varying grain sizes, but a relatively even distribution of grain spacing, and as such pore throats. So when we run the model, which I shall hopefully run, let's have a look. There it is, excellent. So you can start to see, sorry, there we go. So this is the hydrogen traveling through the model, and you can see it travels pretty unhindered to the to the top of the. I'll just play that again. So it travels unhindered really to the top of the model through a few dominant fingers. if we look to the model on the right, oh, there we go, which again, you can see that the pore throats narrow to the top of the model. Oh, my mouse is being a bit difficult here. Let's get that. Oh, you see, I'm getting there. I don't know why that's being so difficult. Okay, here we go. Yes, excellent. Okay, I don't know if people's faces are in the way. Sorry if I'm sharing my screen, you might not see that. But basically, when you run that model, you can see that that travel time is much, much slower for the hydrogen. And it really is, and while it starts with those dominant fingers, it really does slow down as it gets to the top of the, if I can move this out of the way so you can see that. But you can see it's a much slower journey as the hydrogen flow is hindered by by those narrower pore threats. So again, this is starting to kind of confirm that, you know, this capillary entry pressures and these pore throats are really going to have a very important influence on the flow behavior of hydrogen. And as I say, this is in support of the experimental X-ray CT work. So hopefully we can have that working hand in hand sometime soon. Oh, right, there we go. And I did mention that we were doing some reservoir simulation work, and particularly the cushion gases. So another colleague of mine, Nicholas Heinemann, he's been undertaking the reservoir simulation work. And actually started looking at the hydrogen storage in saline aquifers. So that's what this work is the focus of, which again, the publication of this work is on the slide. And what he observed is that pressure dissipation is really one of the main geological processes determining that injectivity and production of hydrogen in a saline aquifer, as I think you'd expect. The large volumes of low density hydrogen in the subsurface, it requires high injection rates and large volumes of pore water have to be displaced. And he also identified that the amount of cushion gas is one of the main factors controlling both injectivity and productivity in hydrogen storage for saline aquifers in particular. And that's going to have a direct impact on that storage capacity of a hydrogen storage site. So the more cushion gas you have, the more hydrogen working gas can be injected and produced, as long as that pressure has enough time to dissipate after the cushion gas injection. So you can read all about that work in this paper. And while I have concentrated on hydrogen storage in porous rocks, which of course is the aim of the HyStorPor project, I just thought at the end I'd highlight a little bit on the salt cavern work that we've been doing. In particular, we've been really focused on offshore salt. We're quite lucky in the UK, I guess. I mean, well, all of our salt caverns at the moment are onshore. And I think that that's going to be an interesting debate about the public acceptance of these, geoenergy applications onshore. So we do also have offshore storage. So I wanted to really get a handle on what capacity and where and how that maps to our existing infrastructure if we were to move offshore for our salt caverns. And actually, we really do have quite a lot of options. We have huge big salt domes. So what we looked at was identified the depth and the thickness of these salts around the UK offshore. So we have a methodology that we've developed to do that. And then, we then, when you find areas that have that optimum depth and thickness, then you can kind of start to understand what that, look in more detail at the geology of those salt deposits to really understand that internal variability, which has a very big impact on cavern engineering, potential for leakage, and all these other things. And actually what we found in these big salt domes, hundreds of terawatt hours of storage exist. And these are actually just a few kilometers offshore of some of our major industrial clusters. So that's quite encouraging. And actually in the UK, we've got Equinor and our one of our electricity suppliers, SSE. They've just announced that they're going to actually repurpose a couple of their onshore salt caverns to store hydrogen. That's to service one of the industrial clusters I mentioned at the very beginning. So they're proposing to repurpose 9 salt caverns, which are currently, well, not currently, but normally used for natural gas storage. And they estimate an initial capacity of around about 320 gigawatt hours of hydrogen storage. So these are really, these are going to be at the forefront of certainly the UK efforts for hydrogen storage. So to summarize, I would say that our findings from HyStorPor are pretty positive for establishing the feasibility of hydrogen storage in porous rocks. and certainly to reduce or manage some of those known uncertainties. We think that, and we feel comfortable that even with further work, we will be able to minimize that risk of biological reaction and hydrogen consumption by selecting sites with temperatures and salinities unfavorable to microbial growth. Whether those boundaries change as we get a little bit more knowledgeable, but I think that they'll still, there will be these limits. We certainly haven't observed any significant geochemical reactions in the 200 experiments we've undertaken so far. We continue to run our experiments, we continue to develop our kind of mineral database, but that certainly is, we're not seeing anything yet. Our column height calculations and diffusion work indicates that hydrogen should have a higher column height to methane, and actually that this column height increases with increasing depth. If anybody is doing any thermodynamic modeling and interested in the kind of thermodynamic property estimations, particularly of hydrogen mixtures, so anybody looking at storing in depleted gas fields or even within the kind of piping system. So Ali has also developed a really nice online tool, which I really highly recommend you use, that it calculates a wide range of thermodynamic properties of hydrogen mixtures. So it'd be hydrogen with CO2, nitrogen, methane, and natural gas over a wide range of temperatures and pressures. Temperatures and pressures that are representative of a storage condition, both from production, all the way from the production, say in the electrolyzers or in the steam reformation, all the way through to the deepest of the stores. And that link is on the slide. So I think that's really quite useful if anybody wants these properties. Certainly our pore scale modeling and our X-ray CT is confirming that importance of capillarity and all its delightful influencing factors. So contact angles, wettability, all of these things are going to come to play, and hopefully we'll have a bit more of an insight into that when Aika's had time to go through all her terabytes of data and look at that. Cushion gas is going to be really important in controlling both injectivity and productivity during hydrogen storage in porous rocks. We really do need a lot of work to tie down these numbers a bit more tightly. And certainly we feel confident that there's going to be plenty storage capacity in our depleted gas fields, even if 80% of it has to be taken up by the cushion gas, and we only have a small working gas. It's still going to be more than enough to supply any seasonal energy storage or indeed export. And I think what's really interesting with the storage capacity work as well is that there's that that we're needing the subsurface for quite a lot of activities, particularly low carbon energy ones such as carbon capture and storage, or compressed air energy storage. And I guess highlighting that hydrogen doesn't need that much or doesn't need that many fields really kind of, I guess, sort of reassures us that it's not really likely to compete with subsurface pore space that's required for CCS. There's plenty of room in the subsurface for all of these energies, and actually I certainly personally believe, just from my work on CCS and on hydrogen so far, that they're going to almost kind of select which are ideal reservoirs. So if we just take, for example, salinity as an example, so for hydrogen, salinity might be a good, high salinity pore fluid might be very positive, because of course that will minimize our risk of microbial activity, and hydrogen dissolution isn't such a big problem. Whereas for a CCS storage site, you don't really want a very highly saline pore fluid, because of course that reduces your dissolution almost by half with small changes in salinity. So that might mean that the more saline pore fluid reservoirs would be more suitable for hydrogen storage than they might be for CCS. So I think there's going to be some really interesting things that shake out as the work progresses. And we've still a lot to do. The second half of the project is going to really look at that flow and transport. So micro CT experiments. We're going to continue with the reservoir modeling and really start to understand in a little bit more detail. We haven't been able to get out and speak to people about for the citizens and opinion shapers and how they feel about hydrogen storage. But we're certainly hoping to get that underway as things come to, as people come back to work. So that's me. I'm not sure of the time. I hope I haven't taken up too much time, but yeah, thank you, and I'd be very happy to answer any questions.
Thanks for the awesome talk, Katriona. That was really well done. I learned a lot in that one. I see that there's a number of questions in the chat. So Todd was the first to ask a question. So Todd, would you like to unmute and ask your question, or?
Sure. I was just kind of curious about what cushion gases were being considered in their reactivity in this situation.
Absolutely. So yeah, thanks, Todd. This is a one we debate quite a lot. So of course, for the depleted oil and gas fields, I think that it's unavoidable that methane will have to be part of that picture. Certainly for the saline aquifers, Nicholas would certainly lean towards hydrogen. Yes, it's a big capex, but then you're not having that risk of mixing. So that, so if you're starting from scratch, maybe your hydrogen may be a suitable capex. But there's also one which we kind of hover around because we're quite interested in it, which is using CO2, of course, as a cushion gas, because that changes the dialogue of CO2 from a storage, from waste in a way to more of an operational kind of working, a sort of operational. You need it in the subsurface as a cushion gas. It's not a waste product anymore. So it changes that dialogue around CO2 storage. But of course, with CO2 storage comes quite a lot more problems with reactivity, with its impact on the microbes, because if you're feeding them both CO2 and hydrogen, they're going to be really happy. So it's a really interesting one, that cushion gas. And I think there's still a lot of work to do on that one, Todd. But I would say at the moment, the leading methane, because if we're looking at depleted gas fields, hydrogen is probably suitable. Some people use nitrogen, but that's another one. So in our thermodynamic property work, we've considered CO2, methane, and nitrogen and hydrogen, and that's why we included those in the mixing ones, because that was to look at, that was also to support people who were doing work on cushion gas mixing.
Thanks.
No problem.
The next question is from JP. JP, do you want to unmute?
Sure. I'd like you to comment on the trade-off between, going deep to avoid microbial activity and the problem of compression cost. If you go too deep, the compression can be too expensive. And I have a second question, which is, you did a lot of experiments trying to see if microbes would be active, in an autoclave, but microbial consortia are fairly picky. So don't you think that, field experiment or control releases are probably the best way to go?
Absolutely. Yeah. So to go through the compression costs, I completely agree with you. So we haven't done the kind of techno-economic modeling yet of all of the trade-offs within that system. So what we're trying to do is really define those boundaries, which we can then input into the techno-economic modeling. So we're not quite at the stage of understanding that trade-off yet in the costs. So we're really just trying to define what those limits within the reservoir are. So that's going to be really important, and I think understanding that balance of, as you say, going deeper and all of the additional costs that go with that is going to be interesting. But whether it's worth it, because you get that higher energy density, reduced risk of reduced risk of microbial activity, increased kind of caprock sealing. So we haven't done that yet, but I think that's going to be interesting to see how that plays out. As for the microbial work, I absolutely agree. Our work is just the beginning. And actually, interestingly, in the EU high-use pre-project, so in HyStorPor, we haven't done any experiments yet. It's very much based on a desk study. So we haven't even had them in the autoclaves. So we haven't started culturing, growing those cultures, which I know is going to be really challenging. But please do keep an eye out for the high-use project, because we've got all of the oil companies on board who are trying to sample their microbes in their reservoirs so that we can start to look at that and as you say, get a little bit more of an accurate representation of what's down there. So watch this space, I would say, if that's all right. Sorry, I can't answer that now, but it's definitely something that we're doing.
Great, thank you.
Okay, the next question is from Tim. Do you want to unmute, Tim?
Sure. That was an awesome talk. Just maybe rephrasing my question. What are what are acceptable re-recovery rates and losses? And thinking about it, I think maybe, it would be in the sort of the same, idea as the cushion gas, as it's factored into CapEx. But what do you think from, things that are operational and into the future, what's an acceptable re-recovery rate?
Absolutely. So it's a really interesting question, because I was once I was on a panel with Centrica. Now, Centrica operate in the UK, they operated our last porous rock gas storage site, natural gas storage site, which was closed a couple of years ago, and they are looking to repurpose that for hydrogen. So they're trying to get government support so that they can permit that and get that ready for hydrogen storage. So they're on the HyStorPor team, and I remember asking him exactly that same question, because I thought, well, it's best to ask the commercial operators, and he just pointedly said to me, he said, Katriona, if basically said along the lines of, if you put the hydrogen in, you will get it back. So basically, any customer who puts their hydrogen in the reservoir will get it back. So I would say that there's no limit, there's no acceptable recovery rates and losses in a commercial world. But whether they have to absorb that in their costings, it's quite. So it made me kind of see it in a different way, because he was like, well, there will be none. Which is not actually real, that's not what's going to happen in reality. So I think it's really just going to be, once we get these limits in, then we can start doing that techno-economic modeling, and I think that will be where we can really start to unpick all of these relationships and understand that. So it's really hard to say at the moment, Tim. Yeah. But if you ask the commercial guys, they'll say there's no losses.
Of course not. Thank you.
Okay, I think we've got time for the last two questions, probably. Syed, do you want to unmute, please?
Sure. Really nice work and very good studies. Appreciate to have a chance to take a look at this. You mentioned for the geochemical reactions that you waited long and nothing happened. So I wanted to know what exactly that means, like how long. And the main reason is like, I remember, if I'm not mistaken, like in the Schnowit project, the CO2 storage project, they also had the same expectation, but when they waited like a few years, the calcite precipitation became so bad, they have to move to another formation because they lost the injectivity. So if you have comments on that, thank you.
Yeah, no, you're absolutely right. And again, these are early stages. So we've run them up to 6 months. So it's not, it's not the life cycle of a storage reservoir by any stretch of imagination. And we are trying to support that with benchmark modeling as well, because of course the modeling said things would happen very quickly, and we just didn't see that happening in the experiment. So there's definitely a mismatch between what the modeling outputs are showing and what we're seeing in the experiments. So we're really just trying to work on that, trying to benchmark these together so that they at least have some correlation between the two. And then from there, we can then hopefully start to build up a bigger picture. But we need pilot projects. We need to see this happening in the field. There's no getting away from that. You're absolutely right. But there's definitely at the moment a mismatch between what the model expectations from the modeling is and what we find in the lab.
Thank you.
We need to keep unpicking that and get into the field.
Thanks.
So I think we might have time for just the last question from Mohsen, if we can make it quick, and then after that we've got other obligations, so we'll all have to log off. But Mohsen, do you want to unmute to ask a question real quick?
You. Can you hear me?
Yes.
Yeah, thank you. Thank you for a very nice talk. I have a question. You had a slide that was entitled Hydrogen and CO2 Storage, Sharing the Subsurface. But I was wondering if you can maybe comment about challenges for transportation above ground, actually, and are there any commonalities between the infrastructures that are being used for other storage, gases?
Yeah, absolutely. So, I mean, if you're talking about, the transportation, if you're talking about the transportation to the reservoir and also subsurface through the pipework networks. So we do have quite a lot of studies looking at the transport of hydrogen through the existing pipelines. So looking at the vintage and the material selection, and all of these to try and get an understanding of whether the existing infrastructure is suitable for hydrogen transportation. So I suppose I can answer this in many different ways, but first of all is the kind of material properties and the suitability, because obviously people are worried about that hydrogen embrittlement, but that doesn't tend to happen at the storage and transport pressures and temperatures. So that might not be necessarily such a big problem. And that material selection, I mean, we certainly even found it within our experiments that, you know, when we were choosing our steel for our vessels, for example, for our high pressure vessels, we really wanted a steel that had a very high nickel content. So we were looking at above 12% nickel. So we really need to understand that kind of material properties of our existing kind of gas infrastructure. In the UK, we're quite lucky, and our domestic supply has slowly been replaced from our iron mains to polyethylene pipes. So they are suitable for hydrogen transportation. So that's working quite well. So in terms of the materials, I think there's a lot of work going on to establish that. In terms of compressions, flow rates, the suitability of all the valves and the infrastructure to deal with that, that's going to be a lot more challenging, because as a rule of thumb, my understanding is that we have either 3 times the pressure or 3 times the flow rate to transport that equivalent energy, as we do for natural gas. So I'm not sure any of the kind of anybody in the gas transportation network would say, well, I really don't want you putting the pressures up by 3, and the flow rates remain, you know, whether that might cause problems with erosion and whatnot. So I think in terms of the gaps, there's a lot, but there's a lot of work ongoing to that.
Thank you so much. Really appreciate your comment. Thank you.
Okay, well, I think that we are about done with questions now. Thanks again, Katriona, for an awesome talk. And I'll ask everybody else if you can log off, please, so that she can go to her direct one-on-one meetings. And as a reminder, next talk that we have will be on December 3rd. It will be Alton Brown speaking about his work on the Strawn Formation of North Texas. Thanks again, everybody.
Thank you.